Alright guys, so I know I'm not here today, but you are going to talk about electromagnetic radiation and electrons. So last Friday we talked about how light or electromagnetic radiation comes from the moving around of electrons, and that gives us different colors of light as we saw in our flame test. Now today we're going to learn a little bit more about what's going on there. So we're going to start off with talking about electromagnetic radiation. What is this mysterious radiation of electromagnetics, and where does this come from? This fancy word for light and various other waves. Well, let's start off with the very essential question: what is electromagnetic radiation? Electromagnetic radiation, or the electromagnetic spectrum, is energy that can travel through space that has wave-like and particle-like properties. So it's like your lights, your UV lights that, mutate your DNA and make you have skin cancer, microwaves that Romeo uses to pop that horrible smelling caramel corn in my classroom during lunch. All of those things are different types of electromagnetic radiation, but we are concerned with the light type, that kind you can see. So let's talk about this light stuff. You can see here, we put white light into a prism over here, and then it comes out a rainbow of separated wavelengths, because there's things in light called wavelengths, and we're going to get into that later. But we're going to focus on the wave properties of the electromagnetic radiation rather than the particle properties. A particle of light would be called a photon, which is a packet or a particle of electromagnetic radiation, but we're more concerned with the waves right now. Where does the electromagnetic radiation come from? Well, as we learned on Friday, when you have an electron that gets excited from one state and jumps away from the atom into another state, and then gets tired and then comes back to the nucleus, it farts out a photon of light. And so depending on what the energy change between the electron's energy states is, whether it's like 1 over here to 3 or 1 to 4, that's going to give us different colors of light. So yes, here it is. Your electron gets excited and then it absorbs energy. Let's say we're heating it up like we did with the flame test on Friday, and then when it's not excited anymore, it goes down, it farts out its little light, and that's where light comes from. It's really exciting. Electromagnetic spectra, what are these things? This is what we use to collect data from light. So we have light. There's different colors of light, as we've seen, like your weird little lamps out in the street. Street lights, that's what they're called. And we want to know what information this can give us, because we're studying it for a reason, not just because I think it's fun, but there are actually reasons why we're studying the electromagnetic spectrum. So let's start off. Why are there different colors of light? Well, there's different colors of light because light has different wavelengths. So we've got long wavelengths, short wavelengths, and the wavelength is the distance. This is a wave like the ocean waves. And the wavelength is the distance between the two peaks of the wave. So if it's a short wavelength, it has different energy than a long wavelength. So we've got our electromagnetic spectrum. This is what I was talking about, those radio waves, microwaves, infrared radiation, ultraviolet radiation. Visible light is actually just this little chunk right here is visible light. X-rays, gamma rays, all of those rays. And so the more energy our waves have, as you can see up here, more energy they have, the actually shorter the wavelengths are. Look how tiny that is, the space between that two peaks, compared to our radio waves over here, where it's like very long wavelengths, a lot of space between those peaks. And so low energy wavelengths are long, and high energy wavelengths are actually very short. Oh yeah, back to this picture. So depending on the energy of the wavelength, as we saw back here, that depends on actually what color of light we're going to get. So if we go from a low energy to a high energy, we're going to get a shorter wavelength a higher energy wave than if we went from like 1 to 2. So 1 to 4 gives us high energy, 1 to 2 gives us low energy. So less energy, low frequency, which is how often the waves happen, and a longer wavelength. High energy, short frequency, more frequent waves, long or shorter wavelength, not longer wavelength. And these are our visible colors. So let's put it in a nice picture form. I like nice little pictures, and so I made you a nice little picture here. Here's our atom, here's our nucleus there, and then these are the shells that the electrons live in, or their energy level. So here's energy level 1, energy level 2, energy level 3, energy level 4, energy level 5, energy level 6. So if I have an electron that's hanging out in energy level 2 right here, and it jumps all the way to energy level 5 and then falls back down. So we heated it up, it got excited, it went to energy level 5, and then it falls back down to its normal energy state. Then what I'm going to get is a large energy change. So that large energy change is going to give me a small wavelength compared to this one, which just went from on a little trip from 2 to 3. That's a small energy change, which gave me a longer wavelength, 434 nanometers compared to 657. So if you look over here on the right side, I actually just took this little bracket and put them next to each other. Big energy jump, short wavelength, high frequency. Small energy jump, long wavelength, low frequency. And that's really all you need to know. If you learn nothing else from this rambling video that I'm making right now, if you just remember this, you'll probably be solid-ish. Alright, so now that we know that these give us different colors, because also these wavelengths, depending on the wavelength, that changes the color that we're seeing, we can get some information from this. So we've got these things called spectroscopes that work like this. Well, when you put a light through a crystal or a prism, you've probably seen this before, it splits it and turns it into a rainbow, because white light actually has all the colors in it, and when you put it in a prism, they all separate out. And that's why we have rainbows, is because the light is going through a cloud, which is changing and splitting the light. So this is how these spectroscopes work. You have a light source, it goes through a little lens, a slit, that prism splits it off into a rainbow of color. You've got two kinds of spectra. We have some spectra where you look at it and you get these really distinct stripes, which are super cool, and then you have some lights where you look at and you're going to get like a continuous spectra. I don't know if you'll see any of those because Del Lago doesn't use those kind of light bulbs. Maybe if you looked at the sun with your spectroscopes. So yeah, like we said before, because you get different colors depending on how far the electrons travel, you get different spectra. You get these different lines. And so if I were to look at Mercury, I would get these little lines in my spectroscope compared to neon or helium or sodium or hydrogen. So what you guys are going to do today is you're actually going to look at these spectra, if you haven't done it already, and you're going to see the light that those things created and how it gets split up by the prism. And that's pretty cool. And scientists actually use this to study space. So on Friday we talked about, oh hey, we might be able to tell what faraway stars are made out of, depending on like what color their flames are. If you put them through a prism and it splits the lights up into like very specific wavelengths, you can tell exactly what's going on. You can tell exactly where those electrons are. And actually, it turns out these spectra are like little fingerprints. So only neon has this particular spectrum because of the amount of electrons it has and where those electrons are located. Only helium has this type of spectrum. Same reasons, amount of electrons and where they're located. So with that in mind, how could we identify what the sun is made of? Think about that for your homework tonight.